Inspiration can strike from anywhere, a sketch, a photograph, or even an AI-generated image like this one. But how do you take that initial spark and turn it into a real parametric model that you have complete control over? That's the journey we're going on today. I'll show you a powerful 4-step workflow in Grasshopper that gives you the tools to create your own complex organic forms ready for 3D printing. Start by setting initial parameters. These are in the form of number sliders. We have a height, max radius, and a slider for thickness. Next, create a line. Create perpendicular frames along this line. Next, create a set of values for radius. Use range, graph mapper. And multiply the output with maximum radius. Create a circle or circles using the planes and the radius. Loft these circles, and that's the base geometry. Convert the base geometry into a mesh. We use mesh machine. First things first, add a button, number of iterations, set the boundary scale to 0.2, size values to 0.2, boundary distance to 400, length to 100. For fixed curves, extract the top and the bottom circle using brep edges. And the geometry. Reset, it takes a couple of seconds. Use plankton mesh followed by simple mesh component to get the remeshed output. Now, thing to note over here is mesh machine converts brep into a mesh, but look at the gradation. We have smaller edges closer to the fixed curves and longer edges towards the middle. So this value governs the maximum edge length. This value governs the minimum edge length based on the maximum value. So 100 times 0.2 would be the minimum edge length. And 400 is the distance from the fixed curves within which it's going to transition from the minimum value to the maximum value. Mesh Machine plugin does not come with Rhino 8. It needs to be installed separately. For that, you may go to Food for Rhino and look for Kangaroo. Although Rhino 8 comes with a Kangaroo physics plugin already inbuilt, install Kangaroo Physics 0.099 version. Download it, copy the files into the library section, which is the component folder, and copy the user files, which is user object files within this folder, and restart Rhino, you should have access to Mesh Machine. So that's step number 2 complete. Once we have the mesh, we proceed with offsetting the mesh using Weaverbird's offset mesh. Offset distance comes from thickness. So we have the offset mesh over here. Then convert this mesh into a dual using the NGON plugin. This plugin has been provided in the NGON plugin can be downloaded directly in Rhino. You just need to type in package manager. Type NGON, and this is the one you need to install. Remember to restart Rhino after you install this. So we first convert this into a dual. Dual converts these into polygons like this. Then we extract the vertices of each of these polygons using NGON face vertices. Create a polyline and invert this to create closed polylines. Also get the arithmetic mean, which is the center of these individual polylines, using average. So the way this works is it takes all the points belonging to one polygon and it averages it to create a point in the middle. We use this middle point to scale down the polyline and create a opening. Copy the step here. Between the outer polyline and the inner polyline to get a polyline in the middle. And the polyline that we get in the middle is the one we need to scale down to create the opening. To get the center for these curves, for scaling it down, we join these two to get the center point. Now for scaling, depending on the size of the polygon or the distance of the polygon from the boundary curves, we should probably scale it. So one of the approaches I'm taking is to deconstruct the point. Look at the Z values, bottom to top of these center points of these polygons. Take the Z values and if a value is closer to the bottom, keep the opening really small. If the value is at the top, keep the opening really small. If the value is in the middle, use a larger opening size. Remap these values. Here's the source target Use the source domain, and here's the target domain, which is default 0 to 1. Use graph mapper. To get the desired output, I'm going to use Gaussian curve with a condition or an expression where this says the expression is going to say if this value. So what's happening is all of these values starting from closer to 0 to somewhere closer to 1000 are being mapped along this graph. So anything which is closer to 0 in z value is going to get a value which is again closer to 0. And anything which is closer to 1000 is again going to get a value closer to 0. Anything in the middle is going to have a value which is roughly 0.2 to 0.5 or 0.7. Now the condition I want to add, because I don't want a scale value of 0. So the condition I'm going to add is, I don't want a scale value which is negligible. Condition is x is less than y. You make this 0 or make it x. So that means if the value is like 0.002, I don't want that small opening. So rather than that, make it 0. Else, keep it x. And this is that threshold. So I'm going to change this to 0.0. And change this to if. Now we get a bunch of values with some of them being 0. Using scale, here's the curve to scale. Here is the center point. Here is the center point. Here is the factor. And this also needs to be grafted. So when I hide everything, notice that we have larger openings in the middle and almost no opening at the bottom and at the top. This component is red because some of the opening values for the factors are 0. That means there is no polyline. So there are nulls. Before we fix that, let's just merge the outer polyline, which comes from here, the middle polyline, and the inner polyline, which comes from here. Within this, use clean tree to remove any nulls. And remove empties as well. Once done, use prune tree to extract branches that have 3 items. So which are the ones which have these middle polyline, and also extract branches which only have 2. That means they don't have any middle polyline, like the ones on the top and the bottom. For these ones, we have 3 polyline for each, or 3 polylines for each branch. So we first explode them. Simplify it and graft it, and then use path mapper to change this to C E. trim tree, and loft curves to get all your individual panels. Trim the tree further. Use simple mesh such that all individual meshes for each hexagon, pentagon, these polygons combine into a single branch. Also, remember to keep the loft option as straight and convert this into a mesh. Remember to join and weld it. Into a single mesh. So at about, so each of these are a separate single mesh. Now for these, what we do is use list item. Extract the two separately. Now, because they have only a pentagon at the top and at the bottom, a polygon at the top and at the bottom. When I say top, it's the outer shell and the inner shell. We can't really loft it because that would create these intermediate faces, which is going to cause problem when we join the mesh. So we only want a mesh along this polygon and a mesh along this polygon. So we have a polyline over here, the outer one, and a polyline which is on the inner surface. So we again explode the tree, find the average, use something called extrude point, which can be found under surface, extrude point. Here's the base curve, here's the point, and convert that into a simple mesh. Similarly, duplicate the process for the other side. And then just combine it. This, and this. Now, there's one mesh that's missing, and that's the mesh connecting this top and the bottom. This. So, in order to fix that, pan all the way to the left. Isolate the initial mesh, which is the outer mesh, and the offsetted mesh. Get the naked or the mesh edges and extract naked edges. Join those curves. So you get two curves for each mesh, one at the top and one at the bottom. As you can see, 2, 2. Merge them, graph them, simplify it, and loft. Again, remember to set the loft option. To straight. Convert this into a simple mesh. And before converting, just check the output. Yeah, that's fine. This goes and connects as the fourth input. With our mesh ready, or the individual meshes in place, that's the end of step 3. In step 4, we take all of these meshes, use Weaverbird's Catmull-Clark subdivision, set the level of subdivision to 2, and set the smooth naked edges to 0. Now the reason we set this to 0 is to ensure that for each individual polygon, we ensure that these edges are intact. Now, normally in a workflow like this, it's advised to combine the mesh together and then do Catmull-Clark subdivision. But what I want to achieve are these sharp corners for each of these polygons. To get the polygons and the sharp corners, I've ensured each of these mesh are independent, are individual meshes. They are then being subdivided, and once that happens, and we get the output like this with the sharp corners, then we join the mesh. For joining, ensure these meshes are flattened. We unify the normals. We weld vertices. And just as a final check, use kangaroo to check if there are any unwanted naked vertices. Now for this mesh, which is a completely closed watertight mesh, there should be no naked vertices. So this output of naked point should ideally be 0. If it's not 0, there is some issue. So let's look into that. To fix this issue, we need to revisit how we created the top cap and the bottom cap. So rather than using this logic, we use the mesh output over here, which clearly has some naked vertices at the bottom and at the top. Also has some naked vertices in the middle. So to fix those in the middle, we ensure that all of these are merged and welded. Remove this, replace it with Weaverbird's join and weld mesh. Invert this, ensure this is flattened, and at this point just check if there are any unwanted naked vertices. So you should only have naked vertices at the top and at the bottom, but not anywhere in the middle. Right? Now if this is sorted, just go back to the initial mesh, which is this one. Hide this and this. Now with this mesh, you need to ensure this is joined and welded. And get the naked vertices. Kangaroo. This is fine. Actually, we need to go to mesh edges and get the naked edges. Join. So you get 4 curves, 2 at the top, 2 at the bottom. Type area to get their centers. With some issue over there, so choose another method to explode. Average. Use point groups. The distance of 100. I've used a distance of 100 because the height is 1000, and if I want to group these 2 points together and the bottom 2 points together, 100 is a decent size. So take this, get the indices which can be used to extract these curves. Explode these curves. Before exploding. Merge. Ensure these are grafted. Loft. Get these individual faces. Convert this into a simple mesh. Flatten. Now connect this over here. Don't need this. Let's see the output over here. Perfect. So we get these sharp edges at the top and at the bottom. No naked vertices. This is a watertight mesh. And view this clearer. Take it. There's some issue with the mesh normals. Also bake these polylines. There you have it. This output is a completely watertight mesh, which can be confirmed by checking the naked vertices. If the naked vertices are 0, that means it's a watertight mesh. And once created, you may change the graph mapper, although it will be really slow to respond because of all the operations. And there you have it, a powerful 4-step workflow for creating your own stunning parametric luminaires. If you want to dive deeper, reverse engineer the process, and use it in your own projects right away, I've made the final organized Grasshopper file available on my Patreon page. When you become a supporter, you get instant access to this file, plus my entire library of projects we have built on this channel. It's the best way to support the creations of more tutorials and get a valuable professional toolkit at the same time. Thank you for joining me for this video. If you found this workflow valuable, a like and subscribe would be amazing. Let me know in the comments what you plan to design next, and I'll see you in the next video.